Ladies and gentlemen, please welcome to the stage from Predator Cycling, Aram Goganian.
Hi everybody, I'm Aram from Predator Cycling, and we are a custom carbon fiber bike manufacturer. We started Predator Cycling in 2005 with the help of my mom, and started making, she's here too, hi. We started making bicycles out of scandium, aluminum, and some small carbon fiber, which you can see here. We did primarily aluminum lugs with carbon inlays. And then this bike here is our first attempt at a super bike. This is a track bike that we did that is primarily scandium and aluminum, so 7005 series aluminum. That's where we started. We actually started a couple years prior to this because of a off comment that I made to a bike builder, who I told him that it's not that hard to make a time trial bike. And he said, if it's not that hard, you should do it yourself. So I was about 13, 14 at the time, and I did. And we made our first time trial bike about 6 to 7 months later. And then about 4 or 5 years after that, we took our brand to market. Today, 11 years later, we are making full carbon fiber frames in-house, as well as carbon fiber components. We do all of our designing, tooling, and manufacturing in-house. And today, I run the company with my wife and myself. In the last 3 years, we've seen this incredible growth in what we're doing, in how we manufacture, how we do things, how we design. And a lot of it has just been the access we've had to technology. In the last couple years, we actually took on making our own CNC in-house. We built a 4 foot by 4 foot with a 1 foot Z, basic, simple CNC router, and we started using that to make our first molds in-house. About a year ago, we started working with Fusion 360 and designing full T-spline shapes of our frames, and basically taking those shapes and throwing them right into CAM and cutting out molds. So that's where we kind of been messing with a lot of this, I call it, T-spline to production. We design it on the computer, we then go straight to making it. And our first product that's been using this new system that we've come up with on the design, for us it's new, doing that whole workflow, we've come up with a way to use composites to kind of help us with that. And the first product we're taking to market with this system is the Majors. This is the picture of one of the renderings that we did of our new bar. And we have a couple bars up here on display that are using a slightly older system. It's the generation prior to this. The Major is a one-piece bar stem system for a bicycle. And this one is a road bike. Here is another road bike and a mountain bike bar. And the newest one that we're coming out with is going to be actually a track-specific bar. There was a lot of issues with making a bar stem system. Traditionally, there's an issue with the clamping area and where it mounts. If you had a separate unit, it would where the stem and the bar clamp is a major issue. Rider performance is an issue on rider inputs and how that translates to the bicycle. And a lot of that we're able to fix as well as ergonomics in designing it this way. So I'm going to walk you through real quick our design on how we start with this product and how we go and actually manufacture it. So I'm going to go kind of quick just because I have 11 minutes. We start off here with a pretty simple 3D sketch. And this is actually our geometry that will start. This is what starts the entire bar. So we're basically designing this curve for the drop in 2D. And we design this in this particular bar, we design it for UCI regulations, which is the governing body for cycling. So we have to adhere to some guidelines. So we spec that in here and we start. And then from there, we pretty much go straight into sculpting. And we don't really get out of it. So this is our first thing. We basically do a very simple pipe, and that's where the bar starts. And the interesting thing is when you start working with T-splines, it works. What you see when you get this part and how carbon fiber lays on top of it, it's very similar because you're taking a shape and you're curving it around something. And carbon fiber it's a flat woven material that we're bending over a part. So in T-splines, when we see a crease or a mark or like a hard edge, that's going to directly translate to our finished product. We're going to get that same hard edge, we're going to get that same crease and have a problem. So this has been really helpful for us because we can immediately see we shouldn't do that. So once we get here, this is our starting point, and about 8 to 10 weeks later of playing with it, you come to this. And this is our track endurance bar that we've come up with. A lot of the shapes here, every shape on this bar is for a reason. If you look at it, you can kind of see that the drop of the bar is not round. We actually thinned it out on the front profile to reduce the drag coefficient, which is super cool because now we have flow testing on our little tiny computers at work, so we can actually test it to see if it works. And you can see that there's this like dip in the front of the bar. We actually been running some simulations on stress and loads, and we found that by changing the shape, we were actually able to disperse the load that happened in that part and make the part significantly stronger. We've also have a little bit of curve in there to allow for when the rider is not racing and they're riding more relaxed, they can actually be in a more relaxed position because it's actually slightly higher up by about 1.5 centimeters to 2 centimeters. And then when they come down lower, it actually drops down. It gives you a nice little relief so that people can put their arm on top of the bars, and they call this it's a praying mantis position. That's what they call it in cycling. So you'll see a lot of guys on the track do it, and they kind of do this. And they do it to get a little more aero. So what we did is we actually changed the shape of it so that their arm will kind of be encompassed there. And the top has a little flat spot because on the track, we don't have brake levers. So a lot of riders come from the road and want to ride on the tops there. So they have like a handle like here to hold. So we basically molded that directly into the bar. And this is also this is a one-piece, one-shot monocoque part. The rear stem knuckle that will attach like you see here is a separate piece, but we'll still call it monocoque. So this is just a picture of our simulation that we ran on our part. And we could find, in the original one, we ran the original part where we kind of went straight across, we saw that we were getting a lot of load right in the front. It was kind of awkward. We didn't think that we would be getting load there, and a couple of our brake tests that we did, it didn't break where we were showing a load. So we basically dipped it down, shaped it, put a little bit of a twist to it, extended the front nose, and we saw that it dissipated quite a bit. We told the computer that this was steel to get the results, but when we tested in real life, we saw that the data actually came back that it was significantly stronger, and it actually was about 200% higher load to snap it on a drop test than our previous bar. And this bar prototyped came in at 260 grams, where this system is coming at 340 grams. So we were able to significantly reduce the weight of our bars. And then this is the final shape. This is the final one that we went to start molding. Now, the way we go about molding is very different than other people. We're a very small company. To take a bar like this to market with this typical clamshell, latex bladder, pre-preg mold, with all the SKUs that we would need, we would be looking at somewhere between $150,000 to $200,000 in tooling, molds, bladders, replaceable bladders, pre-pegs, ovens, everything to take it. Using our system that we have here, we're doing it for under $10,000. And we're able to achieve a better quality part by having less air inside of the carbon. And we're able to achieve a better inside of the part because we are, well, I'll show you the next step here. This is our mold. And if you look, it's kind of hard to tell, but this is actually slightly smaller than the previous image you saw because we actually build all of our molds to the core of the bar. So we don't build a mold on the outside of the bar. We actually mold it for the inside. And we came up with a pretty cool thermoplastic mix where we can actually inject it into this mold. This is obviously half of it. There's the other half. We basically inject it inside. We control an injection pressure. We also run vacuum through the part, and we control the temperature so that we get minimal shrinkage. For our purposes, we say there's no shrinkage. It keeps within all of our tolerances. And we basically make a core, the inside of the bar. And once this is designed out for the inside, we go ahead and cut it out on our CNC. And we do all of our prototype testing because we were talking about 5 to 6 psi of pressure. Our tooling cost is very low. We actually make all of our prototypes using MDF, which is really cheap. It's great, and it cuts well. So these are our original molds that you can see that come. They all kind of fit together. This will get us typically between 5 and 6 pulls before it dies. Now, this is a very different concept than how most bars are made today, and most bikes are made today. This is a picture of one of a traditional pre-preg system that you see on a mountain bike. You can see here he's taking vinyl bladders that are basically wrapped in pre-preg carbon fiber and goes into this massive steel tool. And once this part goes inside here, you can already kind of see some of the wrinkling that you're going to get. And the way they get it out is by pressure. They basically force it into the part and press it out. You get this tool, it's a CNC piece of steel that's incredibly expensive, incredibly heavy to work with. It's expensive to cut. The machine to cut it is very expensive. And to get the bladders made and done in size is also very expensive. Our system doesn't require that. We can actually cut it out of MDF to start, and once we go to production, we can do it out of a 7075 aluminum to make the production mold so we can produce more rapid cores. Also, our core time is about 10 to 15 minutes to pull it out of the mold. And then, so once you have the core done, we go to our layup. This is a picture of one of our prototypes that we laid. We don't do this exactly anymore, but I didn't have a photo of it, so sorry. We're currently doing our layup schedules based on sleeves, bidirectional carbon sleeves. So we basically define our weave orientation by the circumference of the bar. So it makes it super easy. You can basically lay the sleeve right on, pull it flat, and because it's a bidirectional weave, it's basically the angle of the fiber is defined by the circumference of the part. So you do a simple cross-section of your T-spline shape, and you know your orientations. This is a picture of one of the bars that came out of our prototypes. This is one that came right out of the mold. This is actually version 1, so you can see there's some problems. But we had some issues with our envelopes. But the idea is you have this finished part that now has a core. It's a thermoplastic core wrapped in carbon fiber dry. We then make an envelope that goes around that part, and then we vacuum that part. We then basically pull epoxy through it, which is a standard infusion molding process to make a composite part. And we have a proprietary way of now extracting the air out of the epoxy prior to introducing it and fully vacuuming our entire system. So we have very little air in it. So we actually achieve less than 1%, which is less than 1% air in our part, which is really cool because you actually start getting competitive now with an autoclave part, which is a very expensive, very cool way to make something, but we don't have an autoclave. So we came up with this. The other thing that's very cool is I'm sure a lot of you are familiar with molding, and this typically would be an 8 to 12 piece mold, a metal mold to make this part. Some of you look at it and you're probably going to think it's 6 pieces, which it looks like it's 6, but when you start looking at the surfaces, it's 8 or 12, depending how you cut it. And we're able to do this in the traditional mold. We're able to do it in a 6 piece because of the way we're molding the thermoplastic. And in the future, we could very realistically 3D print the core. And you could make a prototype that day and make a pre-production part. I mean, as fast as you can print it, 6 hours after it's printed, you have a pre-prototype part. So it's super cool. You can also, we're playing with the concept of making our outer envelope 3D printed so that we can have our flow media, peel ply, and final outside tooling to be done out of a 3D printed structure. So the benefits of our system is faster prototyping. You can have a fully prototype part. We do it with MDF and our thermoplastics in about 3 days. We go from T-spline structure to a prototype, and we can do, obviously we can make it much less expensive because we're cutting out of MDF and lightweight aluminums. We can make a much stronger part because we have less air inside of our panels, and it's a continuous part. There's less finishing work. As we start getting with better envelopes, we can have very little finishing work compared to a traditional bagging system. And all of our cores that thermoplastics are using is completely reusable. So we actually about 95% efficient on reusing our cores. So we can, during our final cure, we can actually collect the thermoplastic and reuse it. And our goals for this is to finish testing in the next couple months and get our products, this major, completely done, and to get some third-party testing done to confirm everything we're saying. And we're going to basically move all of our products by next year to this molding system. And that's it. Yeah. Thank you.